In this video, we are going to discuss about the concept of inverse of a function. So to start with, I consider a set A here, which contains three elements, -2, 2 and 0, and another set B, which contains elements 4 and 0. And the function I set up this way, I'm going to say that -2 is mapped to 4, which means f of -2 is 4. Then I say the element 2 is also mapped to 4, so f of 2 is 4, and then 0 is mapped to 0. So I'll write them like this: f of -2 is 4, f of 2 is also 4, and f of 0 is 0. So you can see that there are two x values which are mapped to the same value. -2 as well as 2 goes to 4. So f is a many-to-one function. That is, f is not one-to-one. But you can see that f is at the same time an onto function, because the codomain is set for 0, range is also for 0. Every element in the codomain has a preimage, and therefore it is onto. So this is a one-to-one function but not an onto function. Now I'm going to define a function which will undo what f has done. Like f is taking 2 to 4. So I want a function which will take 4 back to -2. So I'm going to define a function like that, which is defined from b back to a. Let's say it's called g. So g is defined from b to a such that b of 4 is equal to -2. So 4 goes back to -2, but 4 also goes back to 2. So g of 4 is -2, g of 4 is also positive 2, and then g of 0 is 0. Now if you look at this, the function which is undoing what f has done here, which is called the inverse of f, is actually not even a function. Now, why is it not a function? If I want to say that f is a function from b to a, then b becomes the domain for g, because it is defined from b back to a. So b is the domain. So every element in the domain should have an image, and there should be only one image. So 0 has an image and there is only one image. 4 has got two images. So 1x has got two y values. So one of the values in the domain has got two images, and therefore g is not a function. So our conclusion is that if a function is many-to-one, f inverse does not exist. So if a function is not one-to-one, f inverse does not exist. Looking at another situation, we're going to consider a function which is 1, but not onto. So I'm going to set up two sets like that, a and b. A has got elements 1 and 2 in it, b has got elements 1, 4 and 6. And my function is defined this way: f of 1 is equal to 1 and f of 2 is equal to 4. So I write that here: f of 1 is 1 and f of 2 is 4. So this is a 1, function, but you can see that the element 6 does not have a pre-image, and therefore f is not onto. So this is a function which is 1, but not onto. We're going to set up a function g which is defined from b back to a. I call it as g. And what is g doing? G will take 1 back to 1 and 4 back to 2. So g of 1 is 1 and g of 4 is 2. So when you look at this g, which is defined from b to a, it's not a function. Why is it not a function this time? Because one of the elements in its domain, 6, does not have an image, and therefore g is not a function. So my conclusion is going to be that f inverse does not exist if f is not onto. So f inverse does not exist if it is not onto. So for a function to have its inverse, it has to be both 1 and onto. So f inverse x is only if it is both 1, 1 and onto. So that's the final result you need to understand. So we discussed the two cases, and our final conclusion is that f inverse x is only if f is both 1, 1 and onto. And what is that called? Both 1, 1 and onto, injective and subjective, is called bijective. So a function will have inverse only if it is a bijective function. So that's the final conclusion there. This is here we have a question. Show that the function f defined from R to R given by f of x is equal to x square plus 1 is not invertible. Not invertible means it does not have an inverse. So I'm going to check if this is a bijective function, and if I can say that it is not bijective, it is not having an inverse. So looking at the function, I know that it's not going to be 1, 1. So I go for a counter example. I find what is f of 2. F of 2 is 2 square plus 1, which is 5. And also its negative number f of minus 2 is minus 2 square plus 1, which is also 5. So f of 2 and f of minus 2 are same. Therefore f is not 1, 1. And if it is not 1, 1, it's not bijective. And therefore f inverse does not exist, or f is not invertible. So here I have another question for you to pause the video and then try it. The question goes like this. Show that the function f defined from n to n given by f of x is equal to 2x is not invertible. So what you would do is you will check if it is both 1, 1 and onto. If it is both 1, 1 and onto, if it is bijective, it is invertible. But the question suggests that it is not invertible, so definitely this must be not bijective. So you check for 1, 1 first. If it is not 1, 1, you can write your conclusion straight away that it is not invertible. If it is 1, 1, you will go ahead and check if it is onto. If it is not onto, then you will again say that it is not invertible. And to look at the situation, another way of discussing the invertibility of a function. Assume that I have two sets, set A and set B, and I define a function f from A to B. The elements of A are denoted by x and the elements of B are denoted by y, which means f of x is equal to y, x is mapped to y, and g will undo it. G of y is equal to x, and then therefore g must be the inverse of f. But in all the situations it won't be the inverse, because we said the function has to be both 1, 1 and onto, but we are going to test it in another way. Look at this one, g of f. We have seen this before. G of f means a composite function. Composition of f and g is called the g of f. So g of f means g of f of x, which means g of, in brackets, f of x. That's the meaning, g of f of x. And what is f of x? Under f, x is getting mapped to y, or I can say f of x is y. So this f of x will be replaced by y. So this is going to be g of y. And what is g of y? G of y means g is taking y back to x. So g of y has to be x. So look at that. G of f of x is x. G of f is not doing anything to the element. So g of f of any element is the same thing. G of f of 7 would be 7. G of f of 8 would be 8. Such functions are called identity functions. So this is an identity function defined in the set A, which we'll write later. Now I'm going to consider f of g. What's the meaning of f of g? F of g means f of g of y. F of g means f of g of y. And what is g of y? G of y. G is taking y to x. So g of y is x. And what is f of x? F is taking x to y. F is taking x to y. So f of x is y. So f of g of y is y. F of g of 10 would be 10. F of g of 8 would be 8. So f of g of y is y itself. So it doesn't do anything to an element. The element is kept the same. F of g of y is y itself. So then f of g is also called an identity function, which is defined on the set B because it's applying on y. So it's an identity function in B. This is an identity function in A. So let's write about that. Since f of g of x is equal to x, g of f of x is x, g of f is said to be an identity function in the set A. And that's notation for that. I, identity function, and suffix A means it's defined on the set A. And since f of g of y is y, f of g is called an identity function, which is defined in the set B and is written as IB. So if both f of g, g of f and f of g, g of f and f of g are identity functions, then we say f is invertible and g is its inverse. So that becomes another way of checking it. So we didn't check for 1, 1 and don't do in this. So what you do is you define a reverse function, then find what is f of g and check if it is an identity function. Then you do g of f and check if it is an identity function. If both the ways it happens, it's said to be an identity function. So let me repeat that one more time. So to prove that a function f is invertible and to find the inverse, I will define a reverse function g, then find two composite functions. One is g of f of x and the other is f of g of y, and show that both are identity functions, which means g of f of x is x and f of g of y is y. If it happens that way, f is invertible and the inverse of f will be g. So now look at this question. Consider the function f, which is defined from the set of positive real numbers to the set open interval 4 to infinity given by f of x is equal to x square plus 4. Show that f is invertible and find the inverse of f. So we are going to say this standard statement. I'll say let y be any arbitrary element in the range of f. So I'm picking up a random element y in the range of f, which is 4 to infinity. And since y is any random element, or rather y is an element in the range of f, every element in the range is an image. Therefore, y has to be equal to f of x, and that is x square plus 4. So I'm trying to find out a reverse function which will undo what function has done, which will bring all the y values back to x. That means I need to solve for x. Is it possible for me to solve for x easily? Oh yeah, I can just shift 4 to the other side and take square root, so I do that. So I'll say x square is equal to y minus 4. Therefore, x is equal to root of y minus 4. So I found x in terms of y. And I didn't take it as plus or minus. I only took x is equal to root of y minus 4 as x is a positive real number. What I'm going to do is this expression which I found, reverse expression, I'm going to call as a function g. So I'll say now consider the function g, which is defined from 4 to infinity back to r plus, because it is a reverse function. It was originally f is from r plus to 4 to infinity. Reverse function will be from 4 to infinity back to r plus, such that g of y, I call that function as g of y. G of y is equal to root of y minus 4. So this reverse expression, reverse function, I name as g of y. But if I want to prove that this is an inverse function, then I need to show that I can just quickly verify it this way, probably this way. Look at this. This is my first set r plus, and this is my second set 4 to infinity. And I just take a random element from r plus, let's say 1. What's the image of 1 under the function? This is my function. F of x is x square plus 1. So 1 square plus, f of x is x square plus 4. So that is 1 square plus 4 gives me 5. So under f, 1 will go to 5. Now under g, will 5 come back to 1? Let's check. Root of g of y, g of 5, root of 5 minus 4, root of 1, which is 1. Yes, it works. But we didn't prove that g is the inverse. That was kind of verifying that it works. So I'm going to do the actual proof, and I have the function g of y here. I have the function f of x here. F of x is x square plus 4. G of y is root of y minus 1. I'm going to write them again. So I'll write what my f of x is, and I'll write what my g of y is. And I need to show that the two composite functions are both identity functions. So I'm going to do first f of g of y. Now when you write f of g, why do we say y? F of g of y, because it is g of y. G acts first. So that is f of g of y, which is f of g of y is root of y minus 4. Now when I say f of root of y minus 4, which means I am considering my function f of x, and f of x is x square plus 4. So f of a would be a square plus 4, f of b would be b square plus 4, f of anything would be that square plus 4. So f of root of y minus 4 would be root of y minus 4 the whole square plus 4. So that's going to be root of y minus 4 the whole square plus 4. When I square it, the square root will go away. So I get y minus 4 plus 4, which is y. So what I have proved is that f of g of y is y. F of g of anything is the same number. So f of g is an identity function, and that's why nothing is happening to y. F of g is an identity function. So I'll say f of g is equal to iy, which is I of y. Y is the second set, which is 4 to infinity. Or you could just leave it like f of g is equal to iy. So we proved that f of g is an identity function in the second set. Now I need to do the other way around, GOF. Consider GOF. When I say GOF, f acts first. Whatever is the inside function acts first. And f is from x to y. So f GOF of x, which is g of f of x. And what is f of x? F of x is x square plus 4. So I'm going to replace this f of x by x square plus 4. So I'll get g of x square plus 4. Now go back and see what is g of x, g of y. G of y is root of y minus 4. So g of a would be root of a minus 4. G of b would be root of b minus 4. G of anything would be root of that thing minus 4. So g of x square plus 4 would be root of x square plus 4 here minus 4. So that's going to be root of x square plus 4 minus 4, which is root of x square, which is x. So that means GOF of x is to x itself. Nothing happens to x when I apply this function. So that means even this is an identity function. GOF is ix, which is I of r plus the first set. Therefore f is invertible, and f inverse is g of y, which is root of y minus 4.